this right here section. And then station 4, station 5 is my throat, station 6 is my exit. This is actually figure 5.6 in the book. So let's start first by characterizing the ideal ramjet. And then we'll do the real ramjet. So one of the first things I'm going to make as an assumption for an ideal ramjet is, well, gamma is equal to constant. Now, we're not going to solve everything like that. I'm going to start it with gamma being constant, but then we actually start to add heat burn. That changes gamma significantly through the engine. And being, I don't remember whether I have you do it in a homework or project, but I have you change this quite a bit, and it will change your thrust drastically. Gamma and CPs. So gas, the universal gas constant is equal to constant, CP is equal to constant. What other assumption we're going to make? We're going to say, well, P6 is equal to P exit is equal to P ambient. That means I'm ideally expanding through my nozzle there. So if my flow is subsonic and the flow outside is supersonic, and I'm ideally expanding through this, what is the flow Mach number outside here? Is it subsonic or supersonic? Have you worked on the project yet? Or it's too early in the morning? Well, it's always too early in the morning. I only had 3 hours of sleep last night, so. Two. All right.
Same boat.
Ideally expanded, right? Supersonic flow outside. And I'm saying that the exit pressure is equal to the same pressure as the exit of the nozzle. That means everything is equivalent. That means that the velocity has to match the outside. And that means that I'm getting a supersonic flow out of that nozzle. And it's ideally expanded because you could get two options for ideally expanded. You could get ideally expanded subsonic or ideally expanded supersonic. So you have one of two scenarios. Now, given that the aircraft is supersonic, then it's ideally expanded supersonic. All right, so ideally expanded, what else? We'll assume I have no drag across my flame hosers, meaning that, remember problem number 2? 1 second. Problem number 2, for the midterm, you have to do the drag across the flame holder by doing the conservation of momentum. For ideal ramjet, we're going to assume no total pressure loss. Makes your life a lot easier here, but we're still going to be doing the real engine, which is your flame holder drag. Okay, we had a question.
Cross-sectional area, you want to do the same?
Cross-sectional area 1 and 2, yes. And we'll show why right now in an ideal situation.
And 4 and 6?
And no, well, no, not necessarily.
Okay.
Sorry. This is your, this is dictated by your area over A star, right? Depending on your Mach numbers and all that. So we're just trying to, the diffuser, I'm trying to make it easier by visualizing this because if you assume ideal, it's going to be isentropic, and it's just a straight line. Okay, so no total pressure losses. This is the next point, but I just going to say. Diffuser and nozzle isentropic. Okay, so what does this mean about my TS diagram? So if we draw a TS diagram, if I'm starting here at the inlet, right here. What's going to happen? I got isentropic, i.e. no entropy change, through the diffuser, so isentropic expansion. I get to station 2. Then I have a constant pressure heat addition through my combustor. Remember this, we've done this at the very beginning of the semester, constant pressure heat addition. So obviously 2 and 3 are relatively close. So 3, 2, 4, constant pressure. Then isentropic expansion from 4 to 6. So somewhere here is going to be 5. And somewhere here is 6. And I'm going to expand to the ambient pressure condition. So this is P ambient. And this is P stagnation 2, which is equal to P stagnation 4. And that's my ideal cycle for my ramjet. So in general, we want to use stagnation states the max temperature in the engine is actually T04, the stagnation pressure, that's the stagnation temperature at the exit of the combustor, right here. And you definitely need film cooling for a ramjet engine because the temperatures are so extreme. So film cooling allows higher T stagnation 4, and you're going to see that's what you need. T stagnation 4 is on the order of 3,000 Kelvin.
Jesus.
So your metals are actually just melted. Yes. Oh. Okay. So I don't want to spend a lot of time talking about that. But okay, so film cooling is just briefly right here. If I have a wall right here and I have a hot gas that is moving here at 3,000 Kelvin, okay, and this is going to melt under 3,000 Kelvin. So how do I keep it cooled down? I use almost rounded jets, an array of multiple jets that I actually issue them right there. And these are low momentum jets that actually follow the flow path and keep closer to the surface relative to the hot core right here, and they end up shielding my wall right here from the hot gas. So you're using gas to separate away the actual shell. That's very neat when you look at it from detailed perspective, but for that I'm referring to caters. Yes. So,
The what?
like yeah, it's
Hey,
pretty
you
intriguing.
don't want to school? I got it.
So, now that we
Sorry?
find our cycle,
And you get yourself
let's
bitch.
define what are my inputs and what are my desired conditions and recap some of the equations. So, we have independent parameters.
No, dude. I could give it to you later.
Yeah, you said that last Tuesday.
No, tomorrow.
Parameters that I have no control over.
No.
I can control certain aspects of it, but certain aspects are driven by the,
Yeah, bro.
in this case, ramjets are going to be Air Force, Navy, or Army, or DoD in general that asks you for these kind of conditions, unless there's civilian supersonic flows. But Mach, the flight Mach number. That's something that you as a designer are deciding that I want this flight Mach number for my aircraft at these speeds or at these altitude conditions. Okay? Again, as a propulsion engineer, you're also deciding based on film cooling aspects, what is my maximum temperature through my engine. So these are anchor points. These are very critical points that determine the whole engine. Tmax max temperature. Another one that I control, this is the major control knob that you have in the engine. It's your actual fuel that you're putting in and the fuel to air ratio. That's the major control parameter they have. So you dictate the circuit-metric condition or fuel to air ratio. Let's see if the equals 1. And the last one is, well, you only got a specific jet fuel that you could use for this. So therefore, or a prescribed jet fuel, so heat of combustion is actually defined for you by the choice of fuel that you're planning on running in this engine. And obviously, you can't control nature, so you're driven by the fact of altitude, meaning E atmospheric and T atmospheric. So these are sort of inputs that you sort of have to take into consideration. Don't really control much, but they're well fixed within your regime. Now, outputs. Or dependent parameters. Now that's what you're doing as a designer, as a propulsion designer. Or aeroplane designer. Specific thrust, that you control. Propulsive efficiency, overall efficiency, thermal efficiency, TSFC. These are your outputs. We do control those. And we know how to compute each one of them. We can start listing some of the equations. Like specific thrust, we said, well, for a ramjet, it's really 1 plus F multiplied by the exit velocity minus U plus P exit minus P ambient, area exit over M dot. Now, keep in mind, P exit minus P ambient is a critical one here because I have a CD nozzle that my conditions could change. So here they're not equal, or potentially could be equal depending on the condition. If I'm ideally expanded, they're equal, that cancels out. Propulsive efficiency, we said it's tau U. I'm just rewriting the equations again. This is not new. 1 plus F, rate of change of kinetic energy. And that's equal to IU over 1 plus F, Q squared, Q minus U squared over 2. And my thermal efficiency is 1 plus F, Q is squared divided by 2, the fuel ratio, heat of combustion. TSFC is equal to m dot fuel divided by the amount of thrust, which is your fuel to air ratio over your specific thrust. And the overall efficiency is equal to thermal efficiency multiplied by the propulsive efficiency like we discussed. And your fuel to air ratio is a function of your fuel to air ratio, exit velocity, the flight Mach number velocity, the heat of combustion. So, assuming obviously ideally expanded. So these are the dependent parameters. So we'll stop right here. We'll continue going over primarily revising the equations that are applicable to ramjets, and then we'll do an example problem on ideal, and then we go to a real. Now, before we leave, the midterm. We need to decide the date.
We did.
Did we decide it?
Yeah.
Okay, when is it? Because I'm not aware. When is it?
5th. Yeah.
4-5?
2 weeks from today.
4-5?
Yeah.
I thought we should have said that.
Oh yeah, that day.
Yeah, but that's what I said I wanted that.
Jag skulle titta hemma nu. No, the 7.
How many of you want 4, 5? Raise your hand. No, we did. We said we're gonna revisit it.
Wow.
You're tricking me, Hunter. The 7. The 12.
We're finding the 12. 12. The 12.
Okay, midterm to 12.
So 14, no, right?
No.
12 or 5.
Out of town?
Yeah, what's the design competition?
How many of you have seen design in 12 to 14?
Ooh, we didn't like that.
5 people.
Ooh, we didn't like that.
7.
We have the sign competition.
The 5th. So target the 7th?
No. No.
Okay, 7th it is.
Who fucked you over, bro?